We have a theory which is called quantum electrodynamics, which is our pride and joy. It's so successful and it's so wide in its application. And what I would like to tell you about is that theory, how it works, or how it looks like it works, and what the world looks like from that point of view. The physics has got a history, at least its theoretical history, of synthesis perpetually. Of course, the experiment is always finding new phenomena. The problem is to work them together, and sometimes we see that they're different aspects of the same phenomenon. An example is, of course, the simplest and earliest one is that the laws of motion became, in the theory, explained the properties of heat, because heat was motion, and if you knew how motion worked, you could understand the thermal properties. It also explained the properties of sound, which is otherwise a mystery, as the motion of the atoms and waves in the gas. Aside from that, knowing the laws of motion, you had to know Newton, who gave us the laws, worked out the laws of motion, also gave us another theory about the forces between large masses and distances from one another called the theory of gravity. Well, that's just that thing, the theory of gravity, is well known and understood pretty well, but is not what I'm going to talk about. As the time went on, phenomena associated with electricity, rubbing combs in your hair and things like that, and magnetism became interesting to the experimental physicists, and they discovered the relations between them experimentally until they saw, ultimately, they were not two different phenomena, but different aspects of the same thing. Another phenomenon that Newton had studied was light. So without time, it looked at first like there were many things, motion and gravity, electricity and magnetism later, and light. But when Maxwell put together the laws of electricity and magnetism, he found out that the behavior, that the equations that he had produced expectation that would be behavior of waves that would propagate at a speed, which was figured out from electrical measurements, but came out the same as the speed that light actually propagated. And so there was a new theory of light, which is that it was an electromagnetic wave, and Maxwell's great synthesis in 1873 was to connect electricity, magnetism, and light. Light is just one aspect of the electromagnetic wave, which can have different kinds of wavelengths from that point of view. And if you have different wavelengths, if the wavelength is very short, between about 400 millionths of a meter, no, the centimeter, 400 millionths of a centimeter and 700 millionths of a centimeter, then you see it directly with the eye. But if it gets longer, the wave is, well, it's a long end, it's red, and then the other end, it's blue. And if it gets longer than the red, we call it infrared. The rays are there, but the eye doesn't see them. The pit viper has an eye that sees the infrared. And if you go in the other direction, to beyond the violet, then we can't see it again, but the bee has an eye that sees the ultraviolet. And if we go still further to the far ultraviolet, no animal has it that can see it, but we can make instruments that detect it, or photographic plates, and so on, up into X-rays and so forth. And down in the other direction, far infrared, you get into radio waves, and we can build instruments that detect them, and we can use them to advertise soap. In addition, so that is an enormous range of one property, the wavelength. A range of phenomena that's a complete, enormous spectrum. The spectrum we see with the eye is a very narrow range, and it's the entire spectrum. It's all put together with the one theory of electromagnetic waves. I'm going to talk about that part of it. I'm going to call it light, instead of saying electromagnetic radiation. Light is what we see, is only one little part, but from the physicist's point of view, the accident that the human eye happens to be sensitive to waves from here to here is not essential. The phenomena are the same over the whole range, and I'm going to call them all light, but it could be radio waves or X-rays or what have you. Next thing that was discovered was the structure of the atoms, and that, I'd like to remind you that you have, I believe, a Nobel Prize winner from New Zealand before, Mr. Rutherford, who was, I believe, a New Zealander, who worked out that the atoms had nuclei. You know, it seemed always here, I've only been here a few days, everybody's talking themselves down. I thought this would be a happy country, but something's happened to you. You've got plenty of room and not too many people, and it looks like it ought to be good. Anyway, don't forget you had Rutherford, so it's okay. Anyhow, he had a theory he developed our understanding of the atoms as having a tiny core, it's very heavy, with the particles going around it, electrons. Now, supposing that the electrons went around according to the laws of motion of Newton, some properties of matter could be understood, supposing the atoms were made that way. But most of the time it failed. And it became more and more of a crisis in physics to understand what matter was like, because it looked so obviously right that it had to be electrons going around nuclei, and yet nothing worked when you worked it out. And the discovery was made then in the discovery of quantum mechanics, first in the behavior of light and then in the behavior of matter, and finally culminating in 1926 with the full equations of quantum mechanics, which told us that the laws of motion of Newton were not right and had to be modified to other laws, which are quantum laws of motion. And when this quantum laws of motion were applied to electrons to explain the properties of matter, it was a fantastic success. The properties of the atoms can be all worked out mathematically, in principle at least, and the simple atoms in detail. And therefore, the theory behind chemistry, which atoms combine with which, at what rate, and so forth, is in principle. Theoretical chemistry deeply is physics. It's not a joke. The chemist will admit that's exactly his point of view, that the understanding of the atoms in the deepest level is physics, except that the atoms have so many particles in them, it's very hard to calculate what's going to happen, so he has to use a lot of empirical rules to help him. But as far as we can tell, there's nothing about chemistry that's not understood ultimately as the behavior of electrons following the laws of motion of quantum mechanics. This defines the properties of all substances also, and so that the whole theory of the properties of ordinary substances and the chemical properties and so forth have all been reduced to the motion of electrons. In the meantime, the theory of light and its interaction with matter, which was Maxwell's equations, had to be modified to become a quantum theory also. Oh, I forgot to mention that during this time, somewhat to one side of the way I want to go in these lectures, I'm not going to discuss much about relativity, but the theory of relativity was developed, and that just makes it easier for us to guess laws. It tells us if we know how something varies in space, then we know how it varies in time, or vice versa. That there's a nice relationship between the behavior in space and behavior in time, and that it's all sort of different aspects of the same geometrical thing called space-time. At any rate, Dirac, using the principles of relativity and the new quantum mechanics, found a wonderful theory, as simple as possible thing you could write down for the motion of electrons, Dirac's theory of electrons, and that was the situation about 1927 or 8. But the problem of the interaction of electrons with light, which was a complete quantum theory of electrodynamics, in other words, make Maxwell's equations of light, of electricity and magnetism, and the theory of motion of electrons, all into one grand theory, was accomplished in 1929 in the theory that was called quantum electrodynamics. Trouble with it was nobody could figure anything out, or better. When they did figure it out, they got nutty answers. If you didn't do it too carefully, you got a reasonably good answer for a problem. But if you carried it out very carefully, you would get some silly answer like zero or infinity or absolutely absurd results. This strikingly lasted for 20 years while people tried to figure out what the correct theory was. During this time, experimenters were measuring things more and more accurately. The theory of they found a few things with very subtle effects that the theory of interaction of light with electricity should explain. And then they measured them, and they found these effects, but they couldn't explain, that is, the theory didn't explain it quantitatively, because when the people made the calculation, they got infinity instead of the right result. As an example, an electron in a magnetic field precesses at a certain rate, and the rate, according to Dirac, was a certain amount. But he didn't take into account the interaction of electricity and light. And when he took it into account, we knew that the answer should be wrong. Let's say that Dirac's answer was right, but when experiment was made, it came out not to be 1, but to be a little bit more. This number here, the experimenters weren't good enough to tell us exactly. It's somewhere between 5 and 21 here. We write it as 8, plus or minus 3 as the next digit. That means this is not measured accurately. So by 1948, 20 years, we had at last measured something which showed that the original theory was without interaction is incomplete. This is supposed to be the result of interaction. When you went to calculate it, you got infinity. So there was a very strong effort made then in 1948 because of the fact that experiments were showing such accuracy to try finally to get that theory straightened out. And it turned out, surprisingly, it was worked out more or less independently by 3 guys who got Nobel Prizes, one of which you see here. And Professor Schwinger, that's not me, but one of the other ones, first worked out a correct way. We found out that the original theory that was written in 1929 by Heisenberg and Dirac and Pauli was very nearly correct. And the problem was that there was something wrong with the way they handled doing the calculations, and we straightened it out. And then we could do calculations, and Schwinger, for example, calculated this and found out that it was something like this, theoretically. And that was a tremendous achievement. It's a great excitement, because that meant we really understood more subtle details, and that the original theory of Heisenberg and Dirac and so on was fundamentally right, just a little switch on how you calculated things. Now this is the theory, then, that we're going to talk about. This theory has lasted now for 50 years. 30 years. I can't add. From 1979, 1949. Oh, it's 50 years, yes, from the time that Dirac and Heisenberg wrote it, and it took 20 years to figure out how to calculate with it. Then the remaining 30 years, the methods of calculations improved. They calculated things much more accurately, and the experimenters became more and more adept at measuring things. And this particular rate that they measured in 1948 to here, now in 1979, has been measured to be, in fact, 10011596524, and the 4 may not be 4. It could be somewhere between 2 and 6. After all, the more you write it, somewhere you have to stop, right? And this, I write to show you the tremendous achievement of experimenters during the last 30 years in order to test with the precision the correctness of the theory. In the meantime, poor guys using calculators and sweating and writing marks on pieces of paper, so on, calculating the results of the theory under the same circumstances for the same phenomena, produced a predicted value that it should be 6523 within plus or minus 3. Why should the theories have a plus or minus? Well, they get exhausted in computing the number of decimal places that they need to keep up with experimenters. This is not atypical. There are 2 or 3 or 4, perhaps, different places where it's been measured and checked to that degree of accuracy. This degree of accuracy, that number of decimal places, corresponds to a precision something like this. If you were measuring the distance of me to the moon, the question would come up, do you mean from my chin or from the top of my head? The difference between whether it's from the chin or the top of my head to the moon is the plus and minus 2 on the end of that number in proportion, all right? That is to intimidate you that the theory is correct in high accuracy. I don't need to produce a large number of other experimental results. They all have this feature. It is remarkable that at this time it is possible to say that there's no experimental discrepancy known between the predictions of the theory anywhere and the results of experiment. That doesn't mean we can compute everything. The rules of the game by which we make the computation, the laws underneath everything that makes nature work, are simple. It doesn't mean we can really figure everything out. To give an example, if you play the game of checkers, I think you call it checkers here, maybe draughts, something. The rules of the game are very simple. The way the pieces move is simple. And if you want to make it even simpler, make the rule no kings, but when you come to the end of the board, you start at the beginning. It doesn't make any difference. The rules are simple. But imagine a checkerboard with 100 million piece squares on each side. Hundreds of millions of these checkers in different positions moving through the board, taking pieces and being taken from the other. Which way are they going to swirl? Which way is the game going to go? That takes a lot of thinking. difficulty of the rules that's involved, but the multiplicity of its action and interconnections. Matter, as you all know, is made out of atoms and all that stuff, is such a multitude of little particles that in ordinary circumstances, so much is happening that in spite of the fact that the rules are relatively simple, not quite as easy as the checker rules, but pretty easy, it still is very difficult in almost all circumstances to figure out what's going to happen exactly. When we can't figure it out exactly, but can do a pretty good job of approximating, the phenomenon is in the range that we expect. When we have a situation that's sufficiently simple, a corner of the board where there's only a few pieces, then we can compute exactly what ought to happen, and when we do experiments in those circumstances, it fits exactly. And that's all we can say at the moment about this theory. This theory has been designed, was originally designed in ideas of space and time and a geometrical framework. And the question is, how small a scale can we go down to? And during the time of this period of time, we not only tried to measure accuracy, but also tried to see how small a distance the theory would be correct at. And I can only tell you the distance is 10 to the minus 15 centimeters. That means 15 zeros before you get to 14 zeros, before you get to a first digit of distance in centimeters. That thing is that accurate. We know that the laws are that accurate. To put it another way, it used to be thought that atoms were small. That was a limit of measurement. But at the present time, with the new instruments and designed during all this time, we've been able to make instruments that can test this theory down to distances that could be described this way. If the atom is made 100 kilometers on a side, then we're measuring with 1 centimeter accuracy inside. So the theory is right. The distances correspond to a centimeter when an atom is 100 kilometers. So altogether, I can only emphasize with delight and excitement the fact that so much of nature is so accurately describable by one theory. There's an enormous range of phenomena, all the things you ordinarily see. The best way to describe what the phenomena are, colors of things, the softness of materials, the weight of things, the way their temperature, when you change the temperature, how much heat it takes, and sounds, and all these phenomena. The only best way to describe is to describe the phenomena that are not included in this theory. And one of them is the accelerations produced by gravity. The force of gravity is in another theory, gravitational theory, or general relativity. Another range of phenomena have to do with exciting the interior of nuclei, nuclear physics, protons and neutrons, radioactivity, and nuclear phenomena. That excluded, all the rest of the phenomena of nature are contained in this one theory. Now you can see why it is that I feel a bit uncomfortable when someone asks to give a talk, please tell us the latest things, because then I'm talking about our problems that we have in trying to understand the insides of a proton. For example, for a proton, to tell you a contrast, our understanding of the outside of the atoms, the electrons and light that I'm going to talk about, the theory, it's our jewel and great achievement, to the things that people ordinarily have to talk about at these lectures, it's as follows. You take the corresponding number for a proton. I don't remember it. It starts at 273, I think 19, I'm not sure, or is it 2719? I don't remember. And it goes on for a number of decimal places because the experiment that can measure it so well. Now we have a theory of the protons recently developed involving quarks and so on. We can't make any calculations yet. We haven't developed the technique good enough. So the best I could say, really, and probably exaggerating, is that the theory does say that this number should be around 3, and the error, and that's what I think it must be bigger. I can't prove that it's as small as it might be 0.3. That gives an idea of how sloppy our understanding of protons is compared to that joule precision that we understand electrons, all right? So that gives us some idea of why it is I feel so uncomfortable talking all the time about what we don't know much about, and nobody asks me about the stuff we do know everything about. So, therefore, I'm forcing upon you a lecture on the things that we think we know something about. Okay, so that's our job. Now the question is, what am I going to do? I'm going to tell you what the theory is. I'm going to tell you what it looks like, what we do to make the calculation, just what the thing is, because otherwise, how are you going to understand what world picture, in other words, this thing is. And it is a world picture because it describes all the phenomena, except for radioactivity and gravity, in the world. It's a lot of phenomena. It's possible even, it might explain, and should explain, if everything is thoroughly understood, the laughter of the audience when you make a dumb remark. Now, if I'm going to explain this theory, the question is, are you going to understand it? Will you understand the theory? When I tell you first that the first time we really thoroughly explain it to our own physics students is when they're in the third year graduate physics, then you think the answer is going to be no. And that's correct. You will not understand. But this business about not understanding is a very serious one that we have between the scientist and an audience. And I want to work with you because I want to tell you something. The students do not understand it either. And that's because the professor doesn't understand. Which is not a joke, but very interesting, I think. And I would like to explain it. My task, really, to explain all this, is to convince you not to turn away because it appears incomprehensible. That's what it takes 4 years of us to do to the student, is to get him so he doesn't run away because it looks crazy. The thing that's exciting about this is that nature is strange as it can be, in this sense, that the rules that are going to be obeyed, that I'm going to tell you about, by which this stuff is analyzed, by which we understand nature, the rules of the checkers, yeah, are so screwy, you can't believe them. Nevertheless, if you follow out the consequences and see what they do, sure enough, all the ordinary phenomena that happen, you can understand. That's hard to do, because you have to know how to count big numbers and do lots of arithmetic and so forth to see how it is that these rules really explain common experience. That will be more difficult for you to understand. What is not difficult is this. Well, that's difficult enough, yes, because it's so strange, but it's no more difficult for you than for the students, and no less difficult. I know sometimes I hear people coming to my lecture to say, oh, I'm going to come to your lecture, although I know I'm not going to understand anything. It makes me feel bad. Or when they come up afterwards, they say, oh, I enjoyed your lecture. It was lots of fun, but I didn't understand anything you said. I really am trying to make myself clear. So I would like to discuss this with you. Will you please keep coming in spite of the fact that you don't understand it? Because I don't understand it either. And the fun of it is that it's so mysterious. Okay? That's the fun of it. So this business about understanding requires just a few words. And so I'm going to say something about the relationship, and I hope we get some of your cooperation. Sometimes you don't understand because, say, the languages, the fellow comes from America and he talks too fast. That's my fault, and I apologize. I hope it's all right. That's a kind of trivial difficulty, relatively. Next kind of not understanding is because you perhaps use new words. That's an accident that comes because I'm working technically and I use the words every day, and I forget that everybody doesn't know what they mean, and I have to be very careful. Again, my job. And then there's a kind of saying that you don't understand it, meaning I don't believe it, it's too crazy, it's the kind of thing I'm not going to accept it. The other part, well, this kind, I hope you'll come along with me. You'll have to accept it. Because it's the way nature works. If you want to know the way nature works, we looked at it carefully. Look at it, that's the way it looks. You don't like it? Go somewhere else. To another universe where the rules are simpler. Philosophically more pleasing, more psychologically easy. I can't help it, okay? If I'm going to tell you honestly what the world looks like to human beings who have struggled as hard as they can to understand it, I can only tell you what it looks like, and I cannot make it any simpler. I'm not going to do this. I'm not going to simplify it. I'm not going to fake it. I'm not going to tell you it's something like a ball bearing on a spring. It isn't. So I'm going to tell you what it really is like, and if you don't like it, that's too bad, okay? There's also the possibility that you don't understand because you're you get a bit confused and you're sure that you must have misinterpreted what I said or something like that, and you get turned off, and that's, of course, a difficulty. Let me assure you that most of the time you did interpret correctly what I said, because if it does, it's going to be so shocking the way nature actually works that you're not going to believe that either. I faked it. I'm not telling you the full story, that for the students I have another way of explaining it, or something like that. It is not true. I'm going to be honest, okay? So I'm going to ask you to try not to get turned off and not to be afraid. Relax and enjoy it. Realize that nobody understands it. Well, what the hell were my students learning for 4 years if nobody understood it? I'm going to explain. And I'm going to explain by a kind of an example. I like to take the Mayan Indians. They had a writing system, and we know some of the things they wrote were astronomical things. And they had a scheme for predicting many things in the sky, eclipses and so on. Let's take the example of when Venus, which was important to them because it represented evil of some sort, was a morning star and when it was an evening star. So they could predict ahead of time whether this bad influence was going to be in the morning or in the evening. And so they discovered that if they waited, that this cycle of morning, evening, morning, evening, morning, evening, 5 of those occupied just exactly the same time as 8 times a certain period that was important to them, 365 days. It's not exactly a year, and they knew the difference, but they still counted in 365-day intervals, which they called a tune. So they said that 5 of these cycles is 8 tunes. Then they discovered, of course, very quickly that if they did this 5-cycle bit for 8 tunes 10 times, they were off by about 6 days. And so they had a rule for shifting, making corrections as they went along, and thus had a very good way to predict when Venus was coming up. Okay? Now let's look at this thing from a point of view. Suppose that the professors, the priests in those days, who wrote this stuff and taught their students these rules, were giving a lecture to try to explain what they did in order to make these wonderful predictions about Venus. Then, if the fellow was any good at exposition and really knew what he was doing, he would say, what we're doing is we're counting the days, just like you're putting nuts in a pot. And we keep on counting 365 nuts, and then another 365, and another 365, and another 365. The guy says, what a lot of work. And when we get all finished, we say, that's 5 of these periods. Now they understood what he said. That's easy. They did not know a quick and tricky way to add 365 times 8. I'm sorry, I said 5 times. I meant 8 times. The students were learning, in the meantime, the laws of arithmetic, something which is, to us now, because we have public and free general education, almost everybody has to struggle through and learn how to add numbers by a tricky scheme of writing them in place system and making carryings and so on, so that if you buy wine for $4.15 and your meal is $2.87 or vice versa, it costs $7.02. And the girl who does this, the waitress, just an ordinary person, in 2 minutes does that. How did she do it? What is she doing when she's adding $4.15 to $2.87? She's doing this, counting out 415 pennies, then counting out 287 more pennies, and telling you how many pennies you would have got if you counted them all from the beginning to the end. But it's highly educated and very trained to be able to do that with those large numbers quickly. This training is something, in spite of the fact that everybody's got it, it's something pretty good, because in the 14th century, mathematicians they were called who could do that. Almost everybody in our civilization can do that, but I took this example, you can understand what's involved. What the students are taught, you see, in our particular problems now about physics, there are many bigger numbers. The numbers are much bigger. It's hard to, numbers are so enormous you can't count them directly. And so we've invented a fantastic array of tricks and gimmicks for putting together the numbers, adding, counting, checking, and so forth, without actually doing it the way I could describe what we're trying to do. If I say, I draw this and I draw that and I draw this and I draw that and I see where the end point is, we don't actually sit down and draw 7,000 arrows and find out where the end point. We have a way of figuring out where it comes, just like we don't actually count 415 pennies and 287 pennies to find out that you owe me 702 pennies. We do it by another trick. These are the tricks of mathematics, and that's all. So that's the part I'm not going to worry about. We're not going to worry about that. So don't relax. You don't have to know mathematics. All you have to know is what it is. All it is tricky ways of doing something which would be laborious otherwise. So it's true that in the years we have developed enormous abilities in mathematics, and it takes a long time to train the students, and so therefore they're very highly educated in that. But if you ask them why, now we go back to the Mayans, we ask them why, when you fill up a tub 8 times with 365 day markers, it comes out that the Venus is up 5 times. They don't know. They don't understand at all. The more accurately they can do it, the fact that they know that they have to change it by 6 days and so forth, adds nothing to their understanding of it. The student who has learned all this mathematics and is able to make these calculations, not only of Venus, of the Mars, the Sun, the eclipses and everything else, is a super priest. Doesn't know why any better. And if he would explain it's nothing but counting days, he would be reduced to the truth on the one hand and to an honest statement that he doesn't understand it. On the other hand, and could tell somebody all about it who doesn't know how to count all these numbers so trickily and so cleverly as this priest students knew, okay? Now, probably, I don't know about philosophy of Mayas. We have very little information due to the efficiency of the Spanish conquistadores and, well, mostly their priests, who burned all the books. They had hundreds of thousands of books, and there's 3 left, and one of them has this Venus calculations in it. So that's how we know about that. And just imagine our civilization reduced to 3 books. The particular ones left by accident, which ones, see? So, anyway, I get off the subject. I make this up now. What I'm saying now is just a story. Suppose now that the students would discuss, or people would discuss the possible meanings of this. Why? Then they would begin to think about, well, 8 times 365 is 2920. That's got 2 2s in it. Now, 2 is a lucky number, and it has 2 2s in it. And then the 9 represents the god of so-and-so, which is related to Venus, and so forth, and that would be a good argument. Then, but in another city, some other guys getting together who have a different kind of an argument about it. They say, look, now, the fact that there's a 20 at the end, if I subtracted that away first, I get 2,900, which is a especially good number from blah, 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 and so on. And they would have different theories. And then someone would come along and say, you know, it doesn't make any difference which one of these theories is right. We still have this fact to go along with. And that is our modern scientific point of view. In the earliest days of science, we got confused arguing philosophically what was a reasonable reason for nature abhorred a vacuum, or it seemed to be nice that gods were doing it. Different kinds of psychological reasons for thinking it probably is all right after you discovered what it was. These things were never useful for predicting what should happen next, and we soon learned not to make these arguments. It's useless. It doesn't add anything, and so we're not going to make my imaginary Mayan arguments about the various gods that make the numbers. And so I'm left, if I'm a modern scientist, with a description of the situation. All right? Now I prepared the audience. Used up all my time to prepare the audience. Doesn't make any difference. I will continue anyway, in spite of the fact I used up all the time, to describe the theory. And in describing it, I will first describe some part of it. The theory is the properties of light, electrons, and the interaction of light and electrons. It's all one theory. I've cut it into 3 parts that way. And the first thing I'm going to start with is the properties of light. Okay? I'm going to tell you some of the properties of light, and I hope, if I can do it, to get to the key point, and then we'll continue in the following lectures to elaborate on it. First, I don't go through the history of the theory of light. It had various things. The first and most important thing I would say is that Newton found out that what we see as white light is a mixture of otherwise purer stuff that's easy to understand. And if you understand how each of the parts works, you just put the mixture back together again. And then you separate the light in a prism, which is done automatically in Auckland very often, at least as far as I can tell, in rainbows. And the various colored, if you would separate light in a prism and take out the part that looked, say, yellow, then you couldn't separate that any further in another prism. It just stayed yellow and orange. That's called monochromatic light, light of one color. So I'm going to discuss all my phenomena for a while with light of one color because it's simpler. The first thing, Newton believed that light was a corpuscular thing and turned out to have very strange properties from that point of view. And it was then explained that many of these strange properties was because, in fact, it was a wave, which was wrong. It turned out he was right. It was a particle. It is corpuscular. The reason that he said it was corpuscular was based on an incorrect guess as to the behavior of waves, and his argument was wrong, logically. But it turned out in the end that it was particles. Now, how I talk about how I know it's particles is this. If we make an instrument to detect light that's as sensitive as it can possibly be made, we make it more and more sensitive. In fact, this thing is called a photomultiplier. And that's not the only instrument. I just take one for an example. It doesn't make any difference how we do it. When we get to light that's sufficiently weak, an instrument to detect it hears clicks, pulses, as if it was rain falling on something. You can bang, 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 bang. When the light is bright, the rain goes bang, 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 bang. A lot of them. When the light is very dim, boom, 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 boom. Small. The particular boom, booms and the bang, bang, bangs and so forth are completely out of proportion. The actual rate is enormous, okay, and a little bit less when there's less light. It's very difficult to get it to a boom, boom, boom. It could so dark in here you wouldn't know what. But this device, to show you an example of how it works, just so you understand what happens when we detect the weakest possible light, is it works like this. There's a metal plate here made with cesium or something. When light shines on it, it knocks an electron out. Then you have another plate here with a voltage that attracts the electron, so the electron, so to speak, falls. It's attracted and speeds up and hits this plate. When it hits this plate, got about 100 volts of energy, it splatters. Other electrons get knocked out of the 2 or 3, 5 perhaps on the average. Now those are attracted to another plate. And they all go sailing down here with another 100 volts, 5 of them this time, and each one of those knocks out on the average 5 or 6 other electrons. Now I got 25, yeah. And that's attracted to another plate, and that hits those, and so on, and you have maybe 10 or a dozen plates. By the time you get out the other end, you got such a chunk of charge and electrons, so many of them, you multiply 5 times 5 times 5 times 5, you'll be a long time counting pins to discover how much that is. You get such a tremendous pulse that you can, the number of electrons high enough, it can go directly through circuits and so forth and turn on and off switches and do all kinds of things, make voltages to pin, make noises, do everything. It's amplified. Now what happens when we have a device like this and we put it in the dark is it goes click, 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 click. Every once in a while, a light particle comes in, a photon. This is a particle in every sense. The experiments have all the right properties as follows. That if you have a very weak light, and you have one or two, just one of them every once in a while, if you put 2 cells out, and there's just a few of them coming, then it goes on one or the other. They don't go off together. They go off together, you got too many coming, and you can't resolve it. But if it's very weak, the particle is either here or there. And it comes in particle. I don't know how much I can emphasize this, especially to young students who have learned its waves. It is particles in every way whenever you can detect it. It's unfortunate for us that we can see the light. I mean, it's unfortunate for us. No, not quite, not quite. That if we were 10 times more sensitive to light, then in the dark, we would see that what we're seeing is little flashes, little tiny dips, dots of light. The nerve would go off, just like this photomultiplier, in spots. But the human eye is not quite that sensitive and takes 5 or 6 of these particles, photons, 5 or 6 photons to make one nerve fiber go off. So it isn't. So we cannot detect with the eye light quite low enough to notice the fact that it comes in the form of raindrops. All right? Got that? They're particles, right? And you can detect them with an instrument. You can count them, so and so many per second. Bright light, more per second. Dim light, less per second. Okay? Now we start to describe the properties of light a little further. Next property I want to talk about is reflection from a glass surface or a water surface. I believe everybody knows that you can see the sun or the moon, let's say, in the sea as it settles, of course. Reflections are a happy thing in art pictures. The moon's light reflected from the water. You have a window. When you look through a window, there must be millions of examples. Right back there, there's one. You look at a window, you can see through it, but also some reflection. Now already there's a problem, because the light that's reflected is not as intense as the light that's shining. Some of the light goes through the window, say, or through the water down in. Only some of the light comes back. If the light is headed for water, for example, straight down, only about 2% reflects. What does that mean, only 2% reflects? That means that if we had a photon counter here, let's say, draw the experiment so you know what I'm talking about. It's hard to make a water surface that's vertical. Yes, so we'll make the water surface horizontal. And light's coming down, and some of it's reflected, and we put a counter here to see one of those photomultiplier things, and we count the count. And we know how much we should have got, and we find what. How can it be partly reflected? When, I forgot to say when I was talking about the particles, when you have light of a definite color, the energy that the first one knocks out is always the same. Each particle is the same strength. There's not half particles. It's a full photon. What you get is full photons. But you only, if the light is dimmer, what does that mean? There are fewer of them, right? Simple. So, of 100 that come down here, perhaps 4. Now, this way and 96 go through. What determines which 4? How does it, which one that's coming down of the 100 knows what to come back up? All right? So the situation is that the phenomena is probabilistic. It takes odds. It comes down here and has a 4% chance. That's 1 out of 25 trials. Huh? I think you know what odds are. If you have, for instance, a die, and you want to get a 1 and you roll it, well, it doesn't come out so often, but it comes out sometimes, 1 out of 6. And what that means, if you roll die 100 times, let's make it 600 times, a little easy. If you roll a die 600 times, you might get 105 ones, or maybe 92 ones, or something like that, right? You get about 100. And if the numbers were bigger, the accuracy in percentage is bigger, not accurate. So if you have 6 billion, no, not 6, because I got 125, 25 billion of these coming down, about 1 billion will come off. Okay? Now, let's see if the next feature is how can it be probabilistic? Suppose that I had a light so weak that I had only 1 photon coming every few minutes. Will this counter go off, or will the one down here go off? 1 out of 25 times this one goes off. Which time? What determines that? Possible theories. Nothing. Pure chance. The world is made of chance. That would mean that the physicists can't predict the future. It would mean that if you set up an experiment with exact conditions, you cannot predict what happens in the future, because you can't predict whether it's going to go up or going to go down. You just got 4% odds. Your whole beautiful structure of science is reduced to computing odds. Nature, instead of being definite, does everything by chance. Not so good. Other possibilities, there are little spots on here. And the photon has to hit a spot on the surface. Newton had several things. You'll find out later when I give you more phenomena, how these various explanations, which way it's going to go, and why the spot one doesn't work. But I'll give an argument that Newton made about that. He said it can't be that, because, he said, you can polish glass. It's wonderful. I love to read these old guys. You know, they knew you could polish glass, but they had the intelligence to deduce from the fact that you can polish glass that there's no spots on it. Like, why? What's polishing? See, he polished, he carved his own lenses. He ground his own lenses, so he knew what it was doing. He takes a coarse-grained, sand-like stuff, what do they call it, the polishing powder, the grinding powder, and that shapes it. But it cuts fairly obvious grooves. And you take a finer one with finer particles, and you cut the grooves of finer, and you make the grooves finer and finer and finer. And after they're fine enough, suddenly it's smooth, and the light comes right through. When it's coarse, it's bounced around. And so he concluded that light cannot see the grooves, that when I polish it, it's not that it's smooth, it's still bumpy, but on a small scale, whereas when I have the big grains, it's on a big scale. It can't be any different. When I polish with the small grains, it's just a small scale of regularity. But somehow light doesn't see anything on a small scale. Correct. All experiments have shown that this is absolutely not the right explanation. If it was, there'd be all kinds of ways of testing that. I told you we can measure down to 10 to the minus 15 centimeters and so forth, and what would happen would be you'd be able to find some area to focus very carefully the light so that the reflection coefficient would be higher than 1 in 25 because you happen to be near a place where there was a spot. Can't do it. No matter what you do, it's 1 in 25. Other possibility, the light that's coming down here, the photons are doing, like footballs. And they spin. And depending upon whether they hit with the nose point or with the flat point, depends on whether they bounce back. In other words, something inside the photon is determining which way it goes. Again, no. Because if that were the case, the light that went through would be all of a certain kind of football. And if you try the reflection again, you'd expect a different number than 4% because of the fact that they're all lined up, and you can't line light up. You can't fiddle around up here by any kind of filtering that'll change that percentage. All the lights, photons, are identical if they're the same color, as in one color. They're all identical, and they behave with 4%. Are we therefore reduced to this horror that physics has got reduced not to these wonderful predictions, but to probabilities? Yes, we have. That's the situation today. In spite of the fact that philosophers have said it is a necessary requirement for science that setting up an experiment exactly similar will produce results exactly the same the second time. Not at all. 1 out of 25, it goes up, and sometimes it goes down. Unpredictable, completely by chance. All right, I really see you turning off. I can see you say you don't understand me. You can't understand that it could be chance. I don't like it. Tough. I don't like it either, but that's the way it is, okay? I don't understand it either. I don't understand it. It must be that nature knows whether it's going to go up or down. No, it does not be that nature knows. We are not to tell nature what she's got to be. That's what we found out. Every time we take a guess as how she's got to be and go and measure, she's clever. She's always got better imagination than we have, and she finds a cleverer way to do it than we have thought of. And in this particular case, the clever way to do it is by probability, by odds. And so the first aspect I have to tell you about then is that light works by probability. All right? By the way, just incidentally, the wave theory had no difficulty with this at all. Because what happened would be like the waves of something are coming down here, and they shake, and they just keep going, but some of them bounce back. Something like a sandbar sometimes partially reflects the waves in the sea. So some of the energy went back. But the waves don't operate this thing. By the way, when you turn the light on, this might go off at any moment. You don't have to wait for a certain length of time. Of course, there's odds that it goes off at any instant, but it could accidentally go off the moment you open the slit. So it's not a question of waiting for the energy of the wave to pile up or anything. It's hopeless. I have to start with light as particles. Waves explain many things, but not right. It's particles, okay? Okay. It's photons. The problem is they have reflected with probability. Now the next feature, having to do with reflection again, that I would like to describe is something that you're also familiar with, perhaps not so directly, but perhaps you've seen the colors in soap bubbles. It's made out of soap water, which has no color. No color, I've seen the colors. Mix it together, get a lot of soap water together, and look at it. No color. You take oil, which is a sort of a yellow fluid, you know, and it drips with blackish yellow junk. It drips out of an automobile on a rainy day. You must have experience here with that. And you look at the puddle. To your delight, there are colors. Colors. These colors are produced by reflections from two surfaces near each other, very close together. If the surfaces are far apart, we'll discuss it later, the same phenomenon really occurs, but it's much harder to see under normal circumstances. What happens there is that in a soap bubble, for example, there's a layer of water. And so we have two surfaces at some distance from one another, so. And then the photon can either come down here and reflect right away, or it can come down this way and reflect from back there. Okay? Now, as it turns out, it's about the same percent. If it's just water between air and air, it's about the same, 1 in 25 both times. What's the colors? If I'm going to do it with monochromatic light, that light of one color, what can you see in colors? What you see on an oil film, on a mud puddle, or in a soap bubble, when you use light of exactly one color, is not colors, but bands, bright and dark bands. Places where the light is reflected very well, and places where it's not reflected at all, across the bubble. Now, the position of those bands, if you first looked at a bubble with red light, you see bands, black and red bands all over. If you look at it with blue light, you also see blue and white, blue and black bands. But the pattern is not the same. They're displaced from where the red ones were. And so when you have both red and blue, you get purple and red and black and purple and so on. Now, if you add to that yellow with its pattern and so forth, you get all these colors from mixing, okay? So we're going to simplify experimentally, as Newton did, and look at these this reflection. What Newton, most of his experiments he did this clever way. He had a beautiful curved piece of glass, which was a lens, and a flat piece, and put them next to each other. And then this was only a very slight curvature. And so he had this gap between the two. And when he shone light this way and looked at reflected light, which, depending on where you looked, see, this is a cross-section of the lens, which is more completely like that. There is some reflection in here, which is irrelevant at the moment. There's another glass plate down here. When he looked in different places, the light came down all over, and he looked in different places. He was looking at cases that corresponded to reflection with one gap or another gap between the sides. And when he looked at this with monochromatic light, looked down on it, since it was a spherical lens, he saw in what I call bands in the soap bubble, but more organized, he saw rings called Newton's rings, with a black area starting and then red, if it was red light he was using, and black, red, and so forth. These looked like they were coming closer and closer together, but he was a clever man and understood immediately what it meant. If he measured the distance from here to here and plotted the answer for whether it's red or dark against this distance, not against this, instead of measuring away from the center, he measured how far apart these plates were. Then he found, like our friends the Mayans, every time you had 365 points, they got black. In other words, if this was black and this was red, then double that distance was black again, and yes, and triple the distance was red, and 4 times the distance was black, and 5 times the distance was red, and so on, nice and even. In other words, instead of measuring by this distance, by measuring the thickness, you find the following experimental result. Reflection coefficient against thickness between the two layers. Okay? The spacing between, in this case, if it's an oil film bubble, with that's the distance. In this case, it's the spacing between the lens and the plate. And if you could change it, it's harder to change in a soap bubble under control, but it changes automatically as it dries out. You get the following. You get no reflection if the thickness is 0, then you get a strong reflection for a certain thickness, and then if you make it thick, you get no reflection, you get a thickness. Reflection, then you get no reflection, you get no reflection, and so on and so on. And now it's getting thicker and thicker. Does this go on forever? Yep. If you got good enough monochromatic light and get the experiment under control, you can make it go almost indefinitely. You can make this work for distances of a meter or more. Still keeping track whether it's even, odd, bump, bump, bump. Okay? There's nothing. That's interesting. Very interesting. But you know, that's damning. Why? Because what theory were you figuring for the reflection from that? That made the reflection be 4%. The odds, 4%, whatever. You put another layer down here at the right thickness, expecting to get 8%, and you get nothing. How does a layer down here turn off the reflection from the layer up here. Or, if you figure that out, and you make the layer just a little thicker, it doesn't turn it off, but in fact the reflection is more than twice. On this scale here, this line would have been what you would have expected if you expected it always to be 4% plus 4% or 8% from the two surfaces. This is what you would have got if you disregarded all this nonsense that actually happened. By common sense, it reflects with a certain odds, and it reflects from the other surface with a certain odds, and so altogether you got twice as many coming back. This is the twice as many. But for some, if the thickness is 0, you don't get anything. If the thickness, hey, that's not such a bad idea, is it? If you don't have any water there at all, you wouldn't get any reflection. Starts out right anyway. Well, that theory was kind of dumb now that I come to think of it. And that helps to explain Newton's observation: when the distance is too small, the light doesn't know anything about it. If the thickness is sufficiently small, it doesn't reflect. It does exactly the same as if there's nothing there. But the horror of it is, it's all right that it increases as the thickness goes up, but it overshoots, you see. And then it comes back to 0 again when the thickness is just right. It's very difficult to invent a probability thing. If I had these spots on this surface, it's very hard to see how you're going to have spots on this surface, which turns the spots on that surface off when they're the right distance away. And so Newton went a little bit nutty. And he talked about fits of reflection and transmission and so forth. And I would like to now just finish this by telling you what is the answer. Now here's the answer. This is the way we figure this out. It goes as follows. What we're going to calculate is a probability. The probability, if a particular question, and then a probability that this counter goes off. The probability that if I had one photon coming down, it'll come back to this counter. The probability, which is measured by this curve. And here's the way the rule is for finding the probability. Now listen, hold your seats now, hold on. Don't be afraid, just go along, all right? Never mind it, don't like it, huh? Just hold on. It works like this. What you do is you take a piece of paper. A piece of paper has nothing to do with the original thing. The piece of paper is only to make marks on. It's got nothing to do with the light, all right? And I have your following rules. That you make an arrow to represent, well, for each reflection, you make an arrow. This arrow, for example, is for the reflection from the front surface, and this arrow might be the reflection from the back surface. And I'll tell you in a minute how to make those arrows. And then what you do is you tie the arrows together this way. You make one and then the other. All right? That means you make this arrow, and then you put the tail of the other one on the head of that one. There's the first arrow is the reflecting arrow from the first surface. And this is the second arrow is the reflecting arrow for the second surface. And you put these two arrows together by this rule. And then look at how far off you've come to the end, yes? Yes. You count the pins in the hole. You count the number of beans you put in the barrel. I mean, you make these pictures. And then you ask, how big is the circle? In area. That area represents the probability that you get the thing back. If the circle area is big, then you get a high probability. If the circle area is small, you get a small probability. And I just have to say one more thing of how to make the arrows. Answer. Well, the size of the arrow depends upon the particular materials. I won't come into that right now. The absolute size of 4% is another matter. What you do is you make an arrow, and depending upon the time it takes for the light to get from the source where it started to the place where you want to count it, you turn that arrow like a clock, depending on how much time. So if it takes a long time, you see, you start out at the source. There's the arrow for the source, but that's not that's not the arrow you're going to draw. This is just a thinking arrow. And then you say, turn over, ding, 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 round, 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 depending on how much time it takes. At a certain rate, every second it goes around 75,000, goes around a hell of a lot of times. It goes around 1 followed by 15 zeros times in 1 second. But it doesn't take light very long to get to from the source to the but it still turns around a lot of times. You turn it around, okay? It's like the roulette wheel, and then just at the moment it hits the counter, it happens to be sitting at some angle. All right? That's for the reflecting from the first surface. Now, what about, that was supposed to be this one. I've gotten too many arrows on here. What happened is you take the first surface reflection, turn it through this angle depending upon the time, and it ends up here. You say, that's not a very big angle. You said it was a big angle. It is a big angle. You know, if you keep on turning, it can look like a small angle when you're done, but you had to turn around and around and around and around and around, right? You know what I mean. It goes around like a clock hand after 25 years is still saying can start at 2 and end up at 2:15. Yes, 25 years it went around. So here it is, having been turned around a lot of time. Okay, this is from the first surface, I should say. That's the arrow for the first surface. Now the arrow for the second surface, rule. Same as the arrow for the first surface, but in the other direction. It's just an accident. It happens to be the opposite direction it starts because, well, not because. The rule will turn out later. When you go from air to glass, it's one way. From going glass to air, you change it around. Anyway, you start this way for the second surface, and you turn this one. No, which way did I turn? Yes. For the time. And when you get finished with this roulette wheel and the second one, it comes out so. And then you add them together the way I said. You tie one on the other end and make the circle. And that's the laws of light. And that'll tell you whether it reflects or it doesn't reflect. And what difference does it make? Why do I get these ups and downs? Well, sure, if you move this, kept that the same and moved that, what is that going to do to my exercise over here? Answer. The first arrow, the time doesn't depend upon where the other surface is, so it does exactly as I did before. I'm doing the same experiment with the bottom surface a little further along, okay? Top the same place. Now the second one, however, when I went to turn it, it's a little bit further. It takes a little longer to get there, and therefore it's turned to a new position. So this second time, the picture would look, if the thing was thicker, the picture might look like this. Instead of being here, since it had to turn further, perhaps it's turned to here the second time. And then when I add these two things together and tie one on the end of the other, and I'll just do that again here, you see that this line is now a long line, whereas before it was a relatively short line. This, remember, was the answer line. The answer line is a longer line, and the area here is much bigger of this circle, and the probability is larger. And this upping and downing, zing, 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 and the answer comes out exactly predictable just by this little game. All right? Now, that's a shock, huh? You say, yeah, he's going to explain why it's like that. That's exactly what I'm not going to explain. I don't understand it. That's the way it works. What I'm going to do in the next lectures is to tell you sort of the generalization of this. This is a special example for reflection. I'm going to tell you how the rules go about turning arrows. It's in fact somewhat simpler than this example. It's not bad at all. It's easy. It's not hard, but much more generally. And what I've done is this is a prototype of the general result. There is no secret behind it that we can do any better than give you that result. All I'm going to do is generalize it. It's going to sound something like this. This part you needn't understand right away. It's what I'm going to elucidate in the next lecture. The idea goes as follows, in general. It's just a statement, and I'll come back and do it again, so don't worry. To calculate the probability of an event, which can happen in a number of different ways, the probability of an event is always what we call the square of an amplitude. In this model, it means the size of a circle corresponding to an arrow. An arrow is called an amplitude. For every event, you calculate an amplitude, which is an arrow on a plane. The probability is the area corresponding to that arrow. All right? That's the first bit. Second, how do we calculate the amplitude for an event? If the event is simply a photon going from point to another of a definite color, then it's simply an arrow which turns depending on the time. And that's the amplitude. Notice, by the way, if there's no reflections and no trouble, it just turns, the area stays the same, the probability of finding a photon is not altered. Okay, even though the arrow alters, its area is the same. It's when we get in trouble when we have more than one way to occur, then the rule goes as follows. If the thing can happen in more than one way, then you find the amplitude. What that was, the arrow, for each way. See, if it could happen in two ways, you got the arrow one way and the arrow the other way. And if it can happen three ways, if it was a double layer of stuff and so on, then you put another arrow for the third way. Maybe that one's a short one. And if there's a fourth way, you put another arrow. And when you're all finished, you put them tail to tail, all the possibilities, and find the total, what we call the total, or the net result of making all these little arrow steps. And that final arrow is the total amplitude, we say, for the event to occur. The probability is, as always, the area corresponding to that arrow. That's kind of stinky, right? Well, it's fun, and it's strange that nature is like that. And I hope you come back to hear how it works in general, a little bit better statement of this to review it. And one other thing, I am going to try to explain to you how this rule explains several of the ordinary phenomena that you're used to in light, such as angle of incidence equals angle of reflection. On reflection, that light bends as it goes from air to water, and it travels in straight lines from point to point, and so on. It's all hidden in that one rule. And how that one rule carries all this information is part of the next lecture, as well as I would tell you right away one more thing, that this rule, that to figure out what happens in nature, you have to calculate an amplitude, is not just for light. It doesn't make any difference what happens. An electron does something. A nucleus explodes. It doesn't make any difference. How do you find it? You can only calculate the probability it's going to happen. And how do you do that? You can guess. You calculate an amplitude. That's a lousy little arrow. And the probability is the square of the amplitude, we call it. That's really, you should call it, in our case, the circle of the amplitude. The circle that represents the amplitude measures the probability. And that's true not just of light, but of the whole structure of nature as far as we can tell. And although quantum electrodynamics is only about electrons and light, we discovered that part of the rule, at least, is valid also for nuclei, nuclear particles, quarks, and everything else. The thing that is special about electrodynamics is our complete knowledge of exactly what the rules are for drawing the arrows. But the fact that you have to draw arrows and end up calculating probabilities like that, which is such a shocking and horrible form for nature, is something that I will talk about next time in further detail. Thank you very much.
These rotating arrows are all very well, but is there another model?
The question is there another model? Naturally, we struggle to find it. I'll tell you the answer of what's going to be in the fourth lecture. Nobody can find one. It's worse. We're not so dumb. We're pretty advanced compared to the Mayans. We've analyzed it very carefully. We almost prove it's impossible to find one over a wide class of ordinary possibilities. If it's going to be any kind of a model, it's going to be at least as weird as this thing. The reason is that the answers from this are so simple. That is, it looks a little complicated, you're not used to it. But mathematically, those forms and those curves are mathematically so simple, and the rules are so simple, it's hard to make any mechanism at all that can reproduce such simplicity. The Mayan thing was really fairly complicated. The numbers were peculiar. There's no explanation of them. This analogy, our numbers are not peculiar. Those, they have an explanation for. It's a different situation. One more thing about gravity, I would just remind you, we don't really have a good model because what comes to why is it that there's a force inversely as the square of the distance? And what do you mean inversely as the square of the distance? That's mathematical. And Newton was the one who taught us that we can make progress if you stop arguing about that. He said, I make no hypotheses. I don't explain the gravity law. I tell you what the law is. That tells you how the things look, and you can predict where the stars are going to be, and that's the pattern. But I don't, at the moment, know. But he left open the question, just like you asked. Maybe tomorrow somebody will figure it out. On your particular question, it's always possible that tomorrow somebody will figure it out, but it's going to be very difficult and very strange.
Do you like the idea that our picture of the world has to be based on a calculation which involves probability?
Not really. If I get right down to it, I don't say I like it, and I don't say I don't like it. I am very highly trained over the years to be a scientist, and there's a certain way I have to look at things. When I give a talk, I simplify a little bit, I cheat a little bit to make it sound like I don't like it. What I mean is it's peculiar. But I never think this is what I like, this is what I don't like. I think this is what it is and this is what it isn't, okay? And whether I like it or I don't like it is really irrelevant. And believe it or not, I have extracted it out of my mind. I do not even ask myself whether I like it or I don't like it because it's a complete irrelevancy. It's a kind of a dumb answer, but it's true. And when I'm lecturing, I shouldn't have said I don't like it. What I was trying to say is you probably don't like it. There's nothing I think we can do about it. It might have been something else. I don't know how else to express it. It's not really personally a dislike.
Have you left out anything in this lecture which you need to add later?
It's very difficult, and I worked very hard on the lecture to try to use as my examples things that I didn't have to change later, the interpretation slightly. You know, I couldn't get an elementary enough process that I didn't have. Later on, I have to make a little change. You see, we talk and we see as though it's reflected at the surface. Actually, what's really happening, I want a deeper understanding, which I should do later on in the lecture, but I might forget, is that it's reflected because it affects electrons in here, which re-emit light here, or here, or here, or here, or here, or here. And what really is the things that we have to add is not the arrow from here and the arrow from here, but a whole lot of little ones from all the distances from there to there. But believe it or not, you get the same answer. Okay? So what I really ought to do, and I would do if I were doing it correctly, would be to talk about the reflections from every interior part and adding arrows. But I would rather add just 2 arrows the first time than an infinity of them. So I didn't cheat a little bit, but I got myself in a slight hole, which you picked up. The actual reflection is from the material, the electrons in the material. In the case of Newton's thing, it's because the electrons which are reflecting from the glass here and here are interrupted in their pattern, and when you add the arrows, it comes out to be, believe it or not, the same as if you just take a one from here and one from there. Perhaps just for those who can, I don't want to make it too hard, but just to give you a clue of the marvelous way it works. If you added tiny arrows to represent reflections from everywhere, instead of just talking about it reflected from here to here, which is a good equivalent way. But if you took a whole lot of little baby arrows, each one a very, very tiny angle from the other, all the same length, which is the reflections from all these places, you see you generate a circle. And what I was using instead of the circle were the 2 arrows, which were the beginning arrow and the end arrow of the circle. And what you told me is I shouldn't talk about the reflection from the front surface and the reflection from the back surface. I should talk about the reflection of all the stuff in between, but it's equivalent. The net result of going around here is the same as going up here and back on that one. It even accounts for the minus sign at least. That is, the distance from here to here is what you get by putting onto this arrow this one backwards. Well, I got the distance is the same, see? So I got it upside down in my, but this line is the same line as you would get by going in a circle. So it's really reflected from the interior. But in the first lecture, I thought I'd just get 2 arrows instead of an infinite number.
Does your picture apply to anything besides electrons and light?
This aspect is universal over the whole of the world's phenomena, as far as we can tell, not just light and electricity. This phenomenon of drawing arrows and making areas for probabilities. The probability amplitudes, we call them. The amplitude and the probabilities are the squares of these amplitudes or the circles of them. That's universal. The next problem is a rule for how to draw arrows under different circumstances. What kind of arrows do you draw under different circumstances? What are the rules? One of the rules I told you is it turns at a certain rate for light and so on. Those are the rules that we do not know well in the case of the nuclear phenomena. But we know virtually exactly, or at least as far as we can tell experimentally. I lost my numbers. For electrons and light, the rule for how to make the arrows is apparently completely known. Nothing is ever complete. But within the accuracy and so on, it's known. What's not known is the rules for making the arrows when it's protons that are moving around and so on. Okay?
When you are looking at something, do you see only light, or do you see the object?
The question of whether or not when you see something, you see only the light or you see the thing you're looking at is one of those dopey philosophical things that an ordinary person has no difficulty with. Even the most profound philosopher, in sitting eating his dinner, hasn't any difficulty making out that what he looks at perhaps might be only the light from the steak, but it still implies the existence of the steak, which he's able to lift by the fork to his mouth. The philosophers that were unable to make that analysis and that idea have fallen by the wayside through hunger.
Can you tell us whether in the future your theory will be found to be wrong, or is it complete?
No, of course not. How can we know what the final thing is? I tell you only what we know today. Can I tell you more? Do you want me to tell you more? Would you like me to tell you what we know tomorrow? I'm sorry. I have the Nobel Prize from the past, not from the future. I do not know the future. And I answer in a similar way to your likes and dislikes. If you ask me what I think will happen in the future, I'll tell you I do not think. I do my best to understand what supposed to understand what we know so far. I do not know what you're going to discover next, okay? I can't. I know only as you're talking about the edge of the discovery business. And it's impossible to say what's beyond the edge. So I can't answer you, all right? Except to say that the history of physics has been that the things that looked like they were nicely set aside turned out to be erroneous upon further discovery. And since society continues to be vigorous enough in its endeavors to investigate nature, it's almost sure, from a social point of view, not from a theory of physics, that new things will be found out which will not fit in, and we have no way to tell whether some young man, perhaps from New Zealand or somewhere, will find another way or more about this stuff, so it'll have a different picture in the future. Obviously, I can't say. I tell you what it looks like today. You call it my theory. It's not my theory. It's the theory everybody uses.